by factoring it and then looking at the factors. So if I factor this, what can you tell me about those two factors? They're consecutive. And if you think of any two consecutive integers, isn't one of them going to be even and one odd? And what happens when you multiply an even and an odd? It will always be divisible by 2, won't it? Because the even component will always be divisible by 2. I just thought that was interesting because we just talked about it. Well, we talked about it in Precal. That kid was doing it in geometry. But anyhow, that's that. All right, back to the matters at hand. We are still on problem 5, but we are ready for part C. So it says model the data algebraically with linear equations. That just means write the equation in line. And they tell you to use the data from 1954 and 1999. So 1954, I have to do women and men. So women would be 32.3 and men would be 83.5. And 1999 is 58.5. I'm specifically using those ordered pairs because that's what they tell me to use. And why do they do that? We talked about this before. Why are they simplifying our lines by telling us which points to use? Then all of our answers will be the same. Because if you pick a different set of points, your answers will probably be close, but they won't be the same. Exactly, right? Okay, so let's work on writing this equation right here. And let's do them in slope-intercept form. And you can certainly use your calculator. So why don't we have you guys Matthew this first row, and all you guys do the women, and then you guys all do the men. So we don't waste a bunch of time on this. Writing equations of lines. So we should be finding slope first, right? You can go ahead and round it off to like 100 or something. And then pick a point, plug it in, and simplify it. You get 0.58 for your women's slope.
Yeah.
And negative 0.26 for your men's.
2004 is
Wrong number
71.9.
Oh, Lord. 1999, yep, was 74, so all this is wrong. Thank you for pointing that out. Because that now we're gonna change all this. So if you didn't get this, that's okay, because it's all wrong. So let's try again. Does negative 0.21 look better? So does this equation look okay? Is that right?
This is what?
Oh, Lord, what?
Is it negative 0.21 or negative 0.26? 0.21.
Well, it's with, if I use the right points, it's negative 0.21. I had the wrong point up there before.
Oh.
So is this right or is this wrong too? Is that okay? Okay, guys, you only had to do one line. I just did two. Did somebody confirm these are right or they're not right? Okay, all right. Now, we talked about this yesterday. This is a positive slope, which tells us what about the women? More of them are getting jobs, and this is a negative slope, which tells us what about the men?
Less.
Fewer of them are working, right? Now, the last question points out an imperfection in the model. Remember, mathematical models are never perfect. It tells me to say that, but it's true. They're never perfect because the data is never perfect. Now, explain why, or explain what the limitation is of these models. Matthew?
Eventually, there would be negative people working.
Okay.
And
So if we kept going and let X, whatever, eventually these guys are going to get more than 100. We're going to get more than 100%, right? And that would be, these are percentages, so we're looking at a cap on that. And this one is eventually going to go negative. So these do not take into account the real life limitations of the problem. Okay? All right. Next. Oh, now we're just doing some regular solving. Okay. You know how to solve that first one. What are you going to do with that first one? Yes, we're going to square root both sides. Thank you, Sam. So we'll have x plus 11 equal to what?
Plus or minus 11.
Plus or minus 11. Plus or minus 11. There need to be two answers here. So x equals negative 11 plus 11, and x equals negative 11 minus 11. So 0 and negative 22 are our answers. Yeah, that's okay. That's okay. All right, how about B? Solve algebraically. So I know what you'd like to do. You'd like to probably type that in. Some of you are like calculator addicts. You want to type in everything. How do we do this without typing it in? How would we solve this equation? Okay, so we'll move the x over to the other side. Square both sides, but remember when we square both sides, that's what we're doing, literally, squaring the side. So this is going to be 1 minus 2x plus x squared, because it's a FOIL. That's a FOIL. What kind of equation do we have now? Linear? Oh, it's quadratic, yeah, we got the old x squared right there. And when it's quadratic, we can always get it set equal to 0 and use the quadratic formula. Could we also try to factor or try to complete the square if that's what we wanted to do? I don't think either one's a good idea in this problem, so I'm going to stick with my quadratic formula idea. But that's all we have to do, agreed? All right, let's do it. See if we can do it without making, see if I can do it without making a mistake. Is that what you got? Yeah. Now, remember, when you square both sides of an equation, you automatically introduce the possibility of extraneous roots. Okay? So we need to check to make sure that these are both okay. So what's 3 plus root 5 divided by 2? Is that 2.62? More or less. I want you to look at this for a minute. If we take, you said, so one answer was x equals approximately 2.62. Take a look at your original equation. If you put 2.62 here, and if you put 2.62 here, are those going to add up and give you 1? No. So that one's extraneous. 3 plus root 5 over 2 is extraneous. Does everyone see that? Why am I checking my answer? What procedure causes me to always check my answer? Squaring both sides. All right, let's try the other one. 3 minus the square root of 5 equals, divided by 2. That one is 0.38. So if I put 0.38 in here, that one looks like it's possible. So I'll square root that number and add it to 0.38. It won't be exactly 1 because I rounded it off, right? But it's close to 1. So this is the answer to the question.
When is it close to 1?
Well, it's 0.998. And since I rounded this off to the nearest hundred. All right, you good with that? Okay, next, another model is a graphical model. The graph below shows the distance from home against time for a jogger. Using information from the graph, write a paragraph describing the jogger's workout. What do you think? Who has an idea? Hank?
The jogger runs away from home and then goes back and then runs away again and then goes back.
So it's like he or she makes 2 laps. It looks like, or 2, like if you run around your neighborhood twice. When the jogger's going, let's see what you're looking at. When the jogger's going like this, she's getting further away from home. And then what's happening here? She's getting closer to home. So here I am going around the block, but at some point I start moving back toward home again, and then I do it all over again. Everybody understand that from the picture? All right, now we got some vocabulary words. I bet you've seen all those words before. So tell me any of them that you know. Steve,
The vertical line test is like a test that uses the function.
how does it work?
Like
You're right, how does it work?
if you draw a vertical line and then it hits the function twice, or like the line twice, then it's not a function.
Okay, so in other words, you got some kind of, you're testing a graph
Mm-hmm.
to see if it's a functional. So you got some kind of weird thing. And if we want to know if that's a function, we'll do exactly what you said. We'll either do it or imagine it, that we're drawing vertical lines. Now I got the hiccups, great. Down through the picture like this. Notice that each vertical line hits my curve in only one spot. That means it's function. If we had some shape look like this, that would not be a function because it hit twice. Now, that is tied directly to the definition of a function. Because if we examine these ordered pairs, I have no idea what they are, so I'm just going to make them up. I'm going to say maybe this is negative 2, 2, and this is negative 1, 4, and this is 2, 2, and this is 3, 3. Just making up coordinates. If I did the same thing with this one, if this is negative 1, 7, this one would have to be negative 1, negative 4, something like that. This right here is the key to being a function. Tell me what your definition is for a function. A function is a relation in which what? What happens?
All the x coordinates are different.
All the x coordinates are different.
Even though two y values can equal the same x value.
So every x is paired with only one y. As long as you have the meaning there, I don't care what you write for the definition of the function. The idea is it's a set of points. In math, we call a set of points a relation. So it's a relation in which each x value is paired with no more than one y value. Each element of the domain is paired with only one element of the range. No x's repeat. All those things mean the same thing. That's what it means to be a function. So you do not have to know a word-for-word definition. If asked, you need to tell coherently what a function is. In one of my definitions, I said a function is a relation in which each element of the domain is paired with exactly one element of the range. What do I mean by domain and range? Hayden?
Domain, all the x's over here, and all the y.
Exactly. Now, I want you to be careful with that definition because right now it's fine because all of our equations are Cartesian, they're x's and y's. We will change up our coordinate system, so it's probably better to think about domain as being all of the first coordinates, which are also known as the independent variables. So your domain consists of all of the independent variables, and your range consists of all of the dependent variables. When you graph, this is your independent axis, and this is your dependent axis. I am not going to argue with you or make it wrong or anything. If you use the word x and y, it's okay, but just understand that not every coordinate system is x and y. So if we're in the polar coordinate system, you can't be talking about x. Independent variables versus dependent variables. When you look at function notation, which which you have all seen before. F of x. X is the independent variable because doesn't this depend on what you put into it? So x is your independent variable. Y is your dependent variable. These are your domain variables. These are your range variables. This is a single variable. All right, what's next? Mapping. Oh, sometimes when functions are drawn, have you seen them drawn as a mapping before? So, for example, let's just use my function that I have here. If I give you the domain, let's just say -2, 0, and 1, if that's your domain, when you draw a mapping, you simply draw a couple of circles, and you put your domain in the first one, and then you put what happens to it in the second one. So if that's my function rule up there, -2 would get mapped onto 1. And 0 would get mapped onto 3, and 1 would get mapped onto 4. It is completely okay to have a picture like this. Let's say your function is x squared. If my domain is -2, -1, 2, then my range I will map onto, if this is my function, I will map onto 4 and 1 and 4. That is perfectly okay. Because what's repeating in that map? Not the x's, the y's. So that's perfectly okay. What wouldn't be okay is having a map that looks like this. That's not okay, because that represents the ordered pairs 1, 3, 1, 4, and 2, 3. Does that make sense to you? Have you seen a mapping before? Those are ordered pairs. What's wrong with this? The x's are repeating, and they can't. Now, they can, but not if you're going to be a function. So this would not be a function. This one is a function. Now, to save us the trouble of looking up a bunch of stuff in our book, I've written some more terms that we use to describe functions, and I've listed the actual definition. So continuity, there's the actual definition. Increasing and decreasing, there's the definition, and so on. I'll let you know which of those you have to know the definition for. But right now in our lives, most of them, we don't need to know the definition, we just need to understand what's going on. So by continuity, you see different kinds of examples of continuity there. If you were describing to your 4th grade brother what makes a function continuous, you would not use that vocabulary. How would you explain to your 4th grade brother that something is continuous? Joseph? Exactly. In other words, Joseph, I can trace the entire picture without lifting my pencil. There's no breaks in it. That's what continuous means. In layman's terms, that's what it means. So if you have a function that looks like this, is it continuous? Yep, because you drew the whole thing without lifting your pencil. But if you had this one, is it continuous? Nope, because I had to lift my pencil to draw it. It's broken. The points where it's broken, or the x values where it's broken, are called the points of discontinuity. And you can see in your examples that there are different kinds of discontinuity. This one, your book calls an infinite discontinuity. It's an asymptote. I prefer to call it non-removable. It's non-removable. But that's the same as infinite, which your book calls infinite. Non-removable or infinite discontinuities are graphed as asymptotes. How are removable discontinuities graphed? Look at your two removable pictures there. How are they graphed? They don't have asymptotes. What do they have? They have a hole, what's called a hole in the picture. That's called a hole. An open circle. So it's not like, this is serious. This is a serious break. This is, the removable ones are a break, but they're kind of, you just skip over that point. They're not as serious. And then the jump discontinuity, you probably remember from last year. Did you study step functions at all? Have you seen those before?
No.
Oh, Lordy. Okay, well, that's called a step function for obvious reasons. We're going to study it, trust me. But that would be a jump discontinuity, because you got a piece of graph, and then you skip up, or jump up, and you get another piece, and then you jump up again. So that's a jump discontinuity. So look at the pictures. You got a continuous, two different kinds of removables. Do you see the difference between the two different kinds of removables? One has an actual dot at that point. It's above the curve, but it's there. And the other one is just nothing at that point. And you got an example of a jump, and then your infinite discontinuity. Two separate pieces totally. Okay? All right, increasing, decreasing. Again, I'm talking to, you're talking to your fourth grade brother. How are you going to explain that a function is increasing or decreasing? What happens? Exactly. When I draw it, and we always go left to right. Always, always left to right. If your pencil goes up, it's increasing. If your pencil goes down, it's decreasing. Most functions are sum of each. For example, if this is my curve, then I would say I am decreasing on the interval from negative infinity to 0. In other words, this entire part of the curve is coming down, right? But then I am increasing on the interval from 0 to infinity. Most curves have increasing intervals and decreasing intervals. They're going up and down. Now lines are either always going up or always going down. But most things with other exponents are some of both. What do you think it means to be constant? Staying the same. So back to my step function. Here. See this interval right here? That's constant on that interval, right? And it's constant on this one and constant on that one. All right, see examples of the pictures there? Everybody okay? Everybody understand what's going on there? There's examples. Okay. Boundedness. The graphs are actually on the next slide. But I like to think of bounded as having a floor and a ceiling. Now you can have one or the other, so you can be bounded below, that means you have a floor, or you can be bounded above, that means you have a ceiling. If you have both, then you're considered bounded. So let's look at those pictures and see if that makes sense. The first picture is not bounded at all. We're shooting all the way up, we're shooting all the way down. The second picture is bounded below. Would you agree with that? Is there a point which it doesn't go past? Down there? Yep. Then bounded above, not below, and then bounded both. There are 12 basic functions. Remember that BFF sheet I gave you the other day? There are 12 of those guys, and you're gonna have to be able to figure out if those basic functions are bounded or not. You feel like you have a grip on boundedness? Okay. Extrema. Extrema are high points and low points. There are two kinds of extrema. There are local maximums and minimums. Maximums, obviously, a high point, minimums, a low point. And then there are absolute maximums and minimums. So if you have a curve that does a lot of bouncing around, actually, I think I drew one there. Let's just look at that one. Let's look at my little example over here. Doesn't it look like A and E are both minimums? They are low points in that section of the graph. So A is the low point in its section, and E is the low point in its section. So you will label A and E both as local or relative minimums. You can use either word, relative or local minimums. They are both the low points in their little piece of the graph. Oh, C is 2. Yep, didn't see it there. C is 2. So A and C and E, very good, are all local or relative minimums. Which one is the absolute minimum? A. Yep, A is the absolute minimum. So your picture can have lots of local or relative minimums, but it'll have one absolute minimum. Unless there happen to be, I guess, two that are the same distance now. All right, what about B and D? What are those? Local maximums. And it looks like B is the absolute maximum. Oh, wait a minute. Does this curve have an absolute maximum? Why not? Because it goes all, it keeps going. So you've got B and D are relative maximums or local maximums, but there is no absolute maximum because of those arrows. Got it? One of the fun things that you will do in calculus class is learn how to take an equation of something funky like that. We're going to learn how to graph funky things like that this year. But next year, you'll learn how to find the coordinates of those points without your calculator. It's pretty cool. All right, tests of symmetry. There are 4 main things that we want to know if we have symmetry about. And those are the axes, the origin, and the identity line. This line is called the identity. This is the line that if you graph it, looks like this. So we want to know if we have symmetry to any of those things. So I'm giving you a couple of examples, and we're going to go through and talk about how you can algebraically test for symmetry. A lot of times you can just visualize it, but we're going to algebraically test. Okay, so your test for symmetry about the x-axis is change the sign on y. And if you get the same equation, then you have symmetry. I want you to think about that for a second. It makes perfectly good sense because here's the x-axis if I'm symmetric, I have a situation like this, right? And what do I know about both of those? They have opposite y values. So if I can have opposite y values and I can keep the same picture, then I am symmetric. So here, let's change it. Sine on y would give me this equation. Is that the same as the original? It is? Aren't these different equations?
Wouldn't the 5 be negative?
Okay, all I do if I'm testing for symmetry to the x-axis, and I'll give you an example here of one that is symmetric about the x-axis, but change the sign on y and see if the equation matches. This is my original. Does that match this? No. Look, if my equation had been this, do these match? Are those the same equation? Yes. So this is an example of one that has symmetry. Its picture looks like this. It has symmetry about the x-axis. This one does not. When I throw some random equation at you and say, does this have symmetry about the x-axis, you simply change the sign on y and see what happens. If you get a different equation, it's no. If you get the same equation, it's yes. These two are the same. What do you think the test of symmetry for the y-axis is? Change the sign on x. So let's look at our equation. If I change the sign on x and simplify, is that equation going to be the same as the one I started with? It is. So this is a yes. This one has symmetry about the y-axis. Over to the side, I wrote the words even and odd. If you have symmetry about the y-axis, you are even. An even function is any function that has symmetry about the y-axis. And before you start thinking, oh, even numbers, the cosine is an even function. It doesn't have any numbers. Okay, you gotta look at the picture. If you are symmetric about the y-axis, you are even. This one is. Origin, change the sign on both. So my equation would be negative y equals 3 negative x squared plus 5. Now when you simplify that, do you get the equation in the box? Be careful. Do I get the equation in the box? No, I don't. Do I? Nope. Here's an example of one that is. Let's say that's our function. If I change the sign on both, would I end up with the same thing I started with? Yes. If a function has symmetry about the origin, it is called odd. Now ours is not, because we got a no on this. But if it does have symmetry about the origin, it is called an odd function. So this is an example of an odd function. The sine function is odd. Which, by the way, I'm hoping to get on the Math League t-shirts this year. Yes. It'll be what all the cool kids are wearing, so we should order one. All right, and finally, we're testing for symmetry about the identity line. To do that test, this is the identity line. We simply switch x and y.
Wait, what do you switch x and y to do?
You interchange them.
Yeah, but for what?
So this would be x equals 3y squared plus 5. So you substitute x for y and y for x. And we don't get anything close to the same equation, so that's a no for this particular function. Here's one, look at this one for a minute. What if we had x squared plus y squared equals 5? What would happen if we switched those? Same equation? Or this is another one, y equals 1 over x. What happens if we switch those? I know at first glance you think they're different, but aren't they really the same? So that's another example of one that has symmetry to the identity on. Okay, so sometime I'm going to say to you, prove this function is odd. What are you going to do to prove that it's odd? You're going to do a test of symmetry about the origin, and you'll do that by changing the sign on both x and y, right? If I want to know if it's even, you'll do a test of symmetry about the y-axis, which means you'll change the sign on x.
Wait, what do you do for the x-axis then, if the y-axis isn't even?
There's only even and odd. So these, if I want to know about symmetry of the x-axis, I'll have to say, does it have symmetry about the x-axis? All right, I gave you one more equation. Let's see if you can do that. We're going to do our test of symmetry. And our new equation is x squared plus y squared plus 50. All right, here we go. Does it have symmetry about the x-axis?
Yes.
What you do is, if you, some of you just visualize that, but isn't that going to simplify to the same equation?
Yep.
And likewise, won't this one simplify to the same equation? And likewise, won't this one also simplify to the same equation? And finally, we gotta be careful on that one.
No.
I don't think those are the same, are they? Because if I moved from one or the other, if I like get y alone up there, wouldn't it be x squared minus 50?
Yeah.
It's gotta be x squared plus 50. So this one's a no, but all the rest of them were yeses. These were all yeses. All right, now we got asymptotes. We've kind of talked about that. We're going to talk about limit notation, and we're going to talk about where the asymptotes are. So I'm going to hold off on that and do some examples here in a second. Asymptotes can be vertical or horizontal, and for the time being, our asymptotes will be lines, but it is entirely possible for an asymptote to be a parabola shape or some other shape. So be ready for that, because we will have some of those. That notation might be scaring you. Hang on, we're going to talk about it right now. Number 8, describe the end behavior. We have in this picture an asymptote at y equals 2 and a curve that looks like this. What we mean by end behavior is what happens as we continue the curve out toward the ends of our paper, so we just keep going, what is the curve doing? Can you describe in words to me? What is this curve doing? Like if I just kept going, what would it keep doing? Getting closer to 2 on the top of that 2. And here it's getting closer to the same 2, but it's coming in from the bottom. So how we describe that is with limit notation. The limit as x approaches infinity of your curve is 2 from the top. So I just described the end behavior of this end of the picture. The limit as x approaches infinity, right? X approaching infinity of the function. This is a picture of the function. The limit is 2 from the top. On the other side, we'll say the limit as x approaches negative infinity will be what? 2 from the bottom. Now please understand, that has nothing to do with positive 2 or negative 2. This is 2 from the top and 2 from the bottom. This is called end behavior. This is the way we write end behavior. So you'll see that as soon as I'm done talking about this, we're going to go through a problem and we're going to talk about all these things with that particular problem. And one of them will be end behavior, and you will write it this way. This right here never changes. That's how you express end behavior. The limit as x approaches infinity, the limit as x approaches negative infinity. That end and that end. This changes depending on your situation. Okay? All right, let's do the second one. What are you going to say there? The limit as x approaches infinity, so out to the right, the limit as x approaches infinity is 0 from the top. And what's the limit as x approaches negative infinity? 0 from the top again. Okay, so when we write our end behavior, we always write this, and then we talk about, okay, what's happening on each end of the picture. All right, so here we go. Now we have an example. This you have to know. So I'm not going to make you know all of those definitions. They're really hard, wordy definitions, but you have to be able to apply them. So here we go. Let's look at this problem. Tell me what you know about its domain. Domain, remember, is what can x be? In a case like this, we have x and y. What can x be? Tell me about it. What can x be? Joseph? Oh, did I write it wrong? Oh, no, it can't be what?
Negative 3 and,
It can't be negative 3, right? Would everybody agree with that? So when we were little kids, we just wrote something like this. X can't be negative 3. Now that we're big kids, what does that mean x can be? Everything else. Would you agree with that? X can't be negative 3, which means it can be everything else. The very next question says asymptotes. Because, see this right here? That's your vertical asymptote. Your vertical asymptote is x equals negative 3. Whatever x can't be is your vertical discontinuity. You can't ever let x be negative 3. So there's a vertical asymptote there. Now a horizontal asymptote's a little bit trickier. Anybody remember how that works? Yeah, you guys may or may not have talked about this, I don't know. Aiden?
There's a, y equals 1.
No, but it often is. It won't be in this particular problem, but it's often y equals 1, David?
It's like, it depends on like, if the x is squared on top or bottom. So like, I think on this one it'd be the ha is 0, and then like, if it was squared on the top but
Did
not
you
on
say the ha?
yeah,
The horizontal
yeah.
asymptote? The ha?
Yeah.
That's what Mr.
That's
Miller
what Mr.
said.
Miller
In my case, okay, so, no, the ha is not 0, okay? The horizontal asymptote, is 2. Here's why. I want you to just think about this for a second. If I let x be really big, like 1 billion, won't my numerator be about 2 billion? And my denominator will be about 1 billion? So that fraction, 2 billion over 1 billion, is 2. Now I know this isn't exactly 2 billion, and I know this isn't exactly 1 billion, but be honest. If I said to you, Ella, I'm gonna give you $2 billion, but I'm gonna keep 1 for myself, are you gonna be upset? No, that 1 is insignificant. As x gets big, this is the only part of the problem that's important as x gets really big. So that means your horizontal asymptote is at 2. Remember that your horizontal and vertical asymptotes are always equations. You can't write just 2. You have to write y equals 2. So those are my asymptotes. Anybody want to talk about that again? The vertical is pretty easy. The horizontal is a little bit harder. Yes?
When they have like exponents, isn't that a way to figure it out too?
When they have what?
When the x's have exponents.
So if you have exponents, the same rule applies. Your situations will be, I'll make one up here. You could have 3x squared plus 9x minus 2 over 4x squared plus 6x plus 1. If your exponents match, then right there's your horizontal asymptote. Because again, if x is 1 billion, these are totally insignificant, and these are insignificant relative to 1 billion squared. The biggest power is the powerhouse of the problem. So this asymptote would be y equals 3/4. Now, if we had this situation where we had a squared on top and no squared on the bottom, then this would have no horizontal asymptote. It would have what we call a slant asymptote, and we'll figure that out, but it would have no horizontal. Because isn't this the same as having no x squared? And when I compare those, I get 3 over 0, which is not allowed. Now, if I reverse it, let me put my 4 back here, and let's take this one out. Now my asymptote is at 0, because the bottom is going to be way bigger than the top. And when you have a fraction with a big bottom, it's small. So, in answer to your question, it comes down to what the powers are irrelevant, what the powers are. It matters whether they match, or whether the big one's on top or the big one's on the bottom. If they match, then it'll just be that ratio. If the big one is on the bottom, your limit will be 0. But if the big one's on top, then you won't have a horizontal asymptote. Does that make sense to you? Okay. And we're not going to sweat what the power is, because it really doesn't matter. You just look to compare the two. Good. Anything else about asymptotes? All right, the reason that I did that first before I did range is because this can really help you figure out the range. The range, remember, is your dependent variables, or in this case, your y's. I want you to think about it for a second. Whatever this picture looks like, I'm saying it has an asymptote of 2. So maybe the picture looks like this. I have no idea. No idea. We're going to figure it out. But right now, I have no idea. In this. Is it ever going to hit 2? If that's its horizontal asymptote, is it ever going to hit it? So what's your range? Everything except 2. So once you've figured out your horizontal asymptote, then you've got your range. So my range will be negative infinity to 2, or 2 to positive infinity. That's my range. Now again, I don't know that that's what the picture looks like. We're going to figure that out another day, apparently. We've covered a lot of important ground today. Some of you are totally like sleeping. Hopefully, something will soak in. Or you have a long week